everyone. Welcome back to the course Introduction to Multi-Agent Systems. In today's lecture, we'll try to understand what are the factors that actually decide on whether or not consensus can happen in a system. So some of those factors include the initial conditions of all of the agents, the underlying rule that all of the agents use to interact with each other, and also the network topology that tells us how the agents are connected to each other. The focus of today's lecture will be on how network topology affects consensus. So let's get started. Let us start by considering a group of n interacting agents. N interacting agents which are connected over some graph G, say, over a graph G. The discrete time distributed averaging model for the network G is given by, let us start with a very simple rule, which is x k plus 1 is equal to a times x of k. Let's define all of the parameters that we have mentioned here. Xk is simply the state vector at the kth time instant. A is the adjacency matrix of G. Okay, now A satisfies a very important property, which is A is also, the adjacency matrix A is also row stochastic. Just to quickly remind you, in a row stochastic matrix, first of all of the entries of A are greater than non-negative, greater than equal to 0, and the row sums add up to 1, and the row sum is equal to 1, meaning A1n should be equal to 1n. Now, if we expand this expression, so we just wrote down math of it. Now let's understand a little bit more. How does this protocol work? Why do we call it a distributed averaging process? So note that it is simply an update rule. So at every k plus 1th instant, the state vector gets updated to a times x of k, where x of k is the state vector at the previous instant of time. So how does this rule work? Why is it known as distributed averaging? So let's try to answer that now. In order to answer that, let us first expand this expression that we have. Write it as 1. So expanding 1, we get x1 of k plus 1. We can write it like this. So we are simply expanding all of the vectors here. And the adjacency can be written in an expanded form in this manner. Xn of k. Okay. Then For the ith agent, we get the expression that xi at the the state of the ith agent at the k plus 1th instant is simply equal to ai1 x1 of k plus ai2 x of k running up to ain xn of k. This expression, notice that all of these terms add up to 1, meaning that this entire expression is nothing but a weighted average of all of the states in the previous instant. Owing to this, hence, it is referred to as distributed averaging. Distributed averaging. What are we interested in? We are interested primarily in studying the convergence properties of the distributed averaging model. Let us write it. Using tools from algebraic and spectral graph theory. Our primary objective is to analyze the convergence properties of the distributed averaging model. In particular, in today's lectures, we will focus on analyzing the role of network topology. It's highlighted. It's a very important factor which affects the convergence results, and we will show how it does that. In the emergent behaviors of the system. So today's lecture will primarily focus on showing how the convergence properties of the distributed averaging model depends on the network topology of the underlying of the system. Before we get to that, let's do a quick recap of some of the mathematical formulations that we'll be using to, which will help us in analyzing the distributed averaging model. So let's get started. A quick recap. The averaging model requires the adjacency matrix to be row stochastic. A is row stochastic in nature. What does it mean if A is row stochastic? It implies that the row sums are equal to 1, meaning A1n is equal to 1n simply, which implies that 1 is always an eigenvalue of A, irrespective of the network topology. In other words, irrespective of the entries of A, of the specific values of the entries of A. And 1n is the corresponding right eigenvector. Furthermore, the solution of the system is given by this. The system that is given to us is xk plus 1 is equal to a times xk. We have looked at this a few times in the past, so we say x of 1 is equal to a times x0, x2 is equal to a times x of 1, and we can substitute a times x0 in the place of x1, meaning this becomes times x0, meaning a squared x0. Iterating this process, we can directly write x to the power x of k is simply equal to a raised to the power k times x0, which is the solution of the distributed averaging system. So this is a general solution which we'll keep on using even as we try to analyze the role of network topology. However, there'll be more specific conditions which we will discuss later, which will be required to come up with the proofs of the theorems that we'll present. Results, and we'll complete the recap process. Just to remind you, let us say we consider a non-negative matrix A with a dominant eigenvalue which is simple and strictly larger than the rest. Eigenvalue say lambda p is simple. The other is that it is strictly larger in magnitude than the other. In that case, when we are trying to analyze the powers of A and where it converges, we have the following result. K tends to infinity, A raised to the power K, or let us consider the modified matrix A by lambda P. A by lambda P raised to the power K converges to V W transpose. What is V and what is W? V and W are the left and right eigenvectors. For the eigenvalue lambda P. So this result says when we are taking the powers of the A matrix, well, a modified form of A, which is A by lambda P, then it converges to this product. V times W transpose, which is nothing but an n cross n matrix and this allows us to tell, or this tells us exactly where the powers converge, which is something that we'll be using in our analysis. Just to highlight here, V and W are normalized eigenvectors, meaning we also have this condition. This is sufficient information which allows us to start talking about where does the system converge for different kinds of network topology. So let's get started with that analysis. network topology. Let us consider a very simple case where we have only two agents who are interacting with each other and are trying to discuss a certain topic. So we consider two agents who are interacting with each other on some topic. So the states agents, the state vector of the system given by x1 of k, which is the state of the first agent, and x2 of k, which is the state of the second agent, and overall it's given by some x of k. What are the agents trying to do? The agents are basically trying to agree with each other. Again, the primary objective in this case is to, the objective for this part is arriving at consensus among the agents. How do the agents do it? The dynamics of the system is governed by the distributed averaging model. It's a simple formulation of x of k being equal to a times, x of k plus 1 is equal to a times x of k, where A is the adjacency matrix, which is, as before, rho stochastic. And k plus 1 is the state vector of the overall system at the k plus 1th instant. So now, let us pose the following questions. I'll draw 4 different network topologies and we'll try to see which of these configurations can actually achieve consensus. Let's pose this question. Which of the following network topologies lead to consensus? So I've drawn 4 different kinds of network topologies here. What we'll try to do is we'll apply the distributed averaging model on each one of these and try to see which of these network topologies actually lead us to a consensus among the agents. Let's start with the first one. Let me copy it here for use of reference. So the adjacency of this kind of a network topology, the adjacency matrix is given by which looks exactly like the identity matrix. So again, we are interested what happens finally to the system. So we try to check. So let's write it. Interested in the emergent behaviors, or equivalently the steady state. Steady state behavior of the system. So that is right. This is what is interest to us, and we already saw that this is equal to a raised to the power k times x of 0. What is a raised limit? So notice that x of 0 is simply a scalar here, simply a vector here, which does not depend on time. Hence, we first compute the steady state value of the matrix a raised to the power k, and then simply multiply it with x of 0. So let's do that. Limit k tends to infinity, a raised to the power k is nothing but the powers of the identity, meaning it remains equal to a. Hence, this here can simply be written as times, let me expand the state vector also, x1 0, x2 0, which implies that x1 at steady state, let me write it as x1 bar, is equal to x1 of 0, and x2 bar is equal to x2 0. Let's look at the network again. What did we get here? We observed that the system states did not change at all for the system which is for the network topology which is given to us. And why does that happen? So this is a very simple formulation, and it is very obvious that every agent interacts only with itself and not with its neighbors. Hence, their states do not change, meaning some form of connectivity at least is important to achieve consensus. So this motivates us to look at the next kind of topology that we have. Let us now look at the second kind of network topology. Here, the adjacency matrices simply equal to A2 because the second topology, and what does this network signify? If you observe, if we start at 1, we can reach 2. Similarly, if we start at 2, we can reach 1, meaning the network here is strongly connected. Right? Again, we are interested in analyzing steady state behavior of the system. So, and we know that we will need to compute the powers of the matrix A. When we compute it, what you'll observe is limit A2 raised to the power k actually keeps on toggling between two matrices. Toggling between two matrices given by, the first one is the identity matrix and the second is A2 itself. Meaning that the final states of the matrix, write it here, I and A2. Meaning final states have two possibilities. Final steady state behavior. Steady state. Basically, the network does not really achieve any steady state. So we rewrite eventually the final states take the following two values. Simply equal to either this or zero. This would imply that x1 bar is equal to x1 0 and x2 bar is equal to x2 0. This, however, would imply that x1 bar is equal to x2 0 and x2 bar is equal to x1 0. What keeps on happening is that the system actually keeps switching between these two values, which also makes sense in terms of the network topology. So what happens here is one passes on its state, two passes on its state information to one, meaning the state of one becomes equal to the state of two. And one similarly passes on its state information to two, meaning two state now is equal to one's previous state. And this keeps on happening each time. Hence, if you look at x2 0, so initially x2 0 was contained here, it moves to x1 0, then again agent 1 sends the same value to agent 2. So x2 0 keeps on switching in this manner. Similarly, x1 0 also moves in the same manner. So this is a very important example. This tells us something very critical. What does it convey to us? It conveys that the states do not achieve consensus even though the underlying graph is strongly connected. Meaning, strongly connectedness is also not enough. So we have to now look for something more than strongly connectedness. So what would that mean for the network? This brings us to the next topology. The third form was this, where the network, as we can see, is strongly connected again. We can start at 1, reach 2. Similarly, from 2, we can reach 1. However, we see there's also an additional edge here that we have added. So does that help us in any manner? Let's see. This is the third network structure. Again, as before, the network is strongly connected. If you notice, it is slightly more than strongly connected. It is also aperiodic in nature. Why? The network is also aperiodic. How is it aperiodic? Because there are two cycles. The first cycle is this, and the second cycle is this. The length of the first cycle is equal to 1, and the length of the second cycle is equal to 2, which implies that the GCD of 1 and 2 is equal to 1. Hence, the GCD of the lengths of all of the cycles in the network is equal to 1, which makes the network aperiodic. So the question is, does strongly connectedness and aperiodicity, do both of them put together help us in any way? Well, in order to answer that question, let us do the calculations that we have been doing for the other two networks. That is, we start with the adjacency matrix, and as you can see here, A3, it has a self group at node 1, so half, half, and 1 and 0. So eventually, it tends to infinity. 1k x 2k. Or let us directly calculate what happens to a raised to the power k. If you do the calculation, I will not show how you can do it, but through the points that we discussed in the recap at the beginning of the lecture, using those points, you can very easily calculate the powers of matrix A. So I'd suggest the students to pause the video right here and go and do the calculation by itself. I'll just write the final value here. So it converges to this value, meaning that at steady state, the states converge to this value. X1 0, x2 0, which means x1 bar is equal to 5610 divided by 3 plus 1 by 3 times x2 0. Similarly, x2 bar is equal to third of x1 0 and 1/3 of x2 0. Meaning, finally, what we have is x1 bar is equal to x2 bar, which implies consensus between the agents. So finally, we have arrived at a formulation at a topological configuration of the agents, which has led to consensus. Notice that prior to this, we analyzed two different network topologies. Let me show you again. We analyzed two different network topologies. First one is this, and the other one is this. And both of them did not lead to consensus. However, the fourth formulation that we have here leads to consensus, finally. Meaning, network topology plays a key role in explaining or in the convergence properties. However, we notice that there's a fourth kind of network shown here, which also signifies something for in our case. So, without much ado, let us analyze the fourth network as well. Right up. So, notice that this graph is actually weakly connected and contains a globally reachable node. There's a globally reachable node. Is equal to 2. Okay. So again, the same calculations. The adjacency matrix in this case is given by 0, 1. Does the system converge? In order to do that, we again do the calculations of what happens to the powers of A. Again, if you do the calculations by yourself, so please go ahead and do that. Pause the video here, spend a couple of minutes in calculating the powers of A, and finally you will observe that it converges to this value. So where do the final states go from here? Final states are simply equal to this. Times x1 of 0, x2 of 0. Which means that, let's write it here, which implies x1 bar actually equal to x2 bar, and both of them are equal to x2 of 0. Meaning, in this case again, consensus is achieved. However, while consensus has been achieved, there's something which is fundamentally different in both the networks that we have, in network 3 and network 4. Let us observe what is the thing that is different. If we see here, the consensus, the final states of the agents actually depends on the initial states of both the agents. Agent 1 and agent 2. However, if you look at this particular configuration, the final state of both the agents depend on only one of the agents. So topology controls more factors than one. Not only does it decide whether consensus happens or not, it also decides where exactly the consensus happens. Meaning, consensus in the network topology plays a key role in controlling the emergent behaviors of the system. Which leads us to the following questions of importance. For the analysis that we have done so far, based on our analysis, or not really analysis, rather observation of the 4 different kinds of network topology, the following questions arise. What is the first question? In general, for any given network, when can we say when or what kind of network topologies Does the averaging model, does the distributed averaging algorithm lead to consensus? This is the first question. The question is, if consensus is achieved, among the agents, do the values of all of the states all the states converge to a desired value, a desired value? Basically, can we control where does the consensus happen, at what value? Say some xd, which is a scalar, xd bar. In the next lecture, we will try to arrive at answers to these two questions. So what are the network topologies? We already know that network topology does play an important role in determining the emergent behaviors of the system under the distributed averaging algorithm. However, what we do not know precisely is what are the exact kind of network topologies which lead to consensus, and where exactly does the consensus happen, at what value of the states? Can we control that value? These are the questions that we are interested in, and which is also relevant, keeping practical applications in mind. So, something that we'll discuss in the next lecture. This brings us to the end of this lecture, and we'll discuss more in the next lecture. Thank you.